give the brief schedule, and then we will start.
Yes, sir, you can start, I think so. Yes, sir.
I think so. We'll start first with a welcome. I think then next there will be a introduction of our speaker, Dr. Tejas Bhai, and then there will be his speech, and at the end,
Yes.
I think Jitesh Bhai will summarize the things, and with this we end our program. Right? Is it okay?
Yes, sir.
Yes, sir. Yes, sir.
Yeah. Good afternoon, everybody. On behalf of IGS Surat chapter and SVNIT students chapter, I welcome you all to today's lecture by Dr. Tejaskumar Thaker. I think in this series, I say this is our seventh lecture.
Sixth lecture.
Yeah.
Yes,
This
sir.
is our sixth
Sixth.
This is our sixth lecture, and this is how we are trying to share the knowledge of the stalwarts. And today also, the total, I think, 42 participants are there. I think that includes some stalwarts. What I can see is, I think, from Anulab, Dr. Singh is there. I think I have seen the name of Dr. Sawant also. Other name I don't have at present, but I hope that all will take advantage of work done or what the knowledge shared by Dr. Tejas Bhai. So I will request Manali to introduce our guest speaker.
Sure, sir. Good evening, one and all. In our today's webinar series, the guest speaker is Dr. Thaker. Thaker has completed his BTech and MTech from MSU Baroda and PhD in Seismic analysis and microzonation in around Surat region from IIT Delhi. Currently, he is associated with Pandit Deendayal Energy University as the head of civil engineering department. His research interests include mainly in earthquake engineering, including seismic microzonation, earthquake modeling, earthquake resistant design, seismic hazard and risk mitigation, site-specific seismic studies, site characterization, liquefaction problems, geophysical studies, GIS, GPS, seismic modeling, etc. Rather than that, numerical modeling, ground improvement techniques, geoenvironmental and mining problems, rock characterizations. Dr. Thaker has published more than 70 papers in reputed international and national journals and conferences. He has guided 20 postgraduate dissertations and 2 PhD theses. He is present research supervisor of 5 PhD research scholars, winner of L&T Center at PDPU, who developed facilities over 1 crore rupees in various laboratories in civil engineering. He did 8 research funding projects of around 24 lakhs. His biography was appeared in Marik's Who's Who in the World 2013. 30th edition of USA. He also got Young Scientist Travel Grant Award 2 times by CSIR and Center of Urban Earthquake Engineering, Tokyo Institute of Technology, Japan in the year 2010 and 13. Dr. Thaker has also got many Best Paper awards and in national and international conferences. Furthermore, he is also serving as a reviewer in international journals of earthquake engineering, geotechnical and geological journal, etc. He is also a life member of Indian Geotechnical Society, New Delhi, since 2005. He is also a life member of Indian Society for Technical Education, New Delhi, since 2005. He is a life member of Institution of Engineers since 2013. So, with this brief introduction, I welcome you, sir.
Thanks so much, Manali. First of all, it's my great pleasure to deliver a talk at SVNIT, especially in IGS student chapter. I'm really thankful to Professor C.H. Solanki, of course, Hitesh Bhai, who was actually instrumental in and who has helped me a lot while I was working in Surat, and I think he has provided lot many datas while I was working. You can say in Surat. So really thankful. You can say our organizing committee who has actually given the opportunity to talk and present my work today. Let me share my presentation. Yeah, I hope my presentation is visible to you.
Not visible yet, sir.
I had certain network issues here. Okay, so about
Sir, share entire
seismic ground response analysis. So if you talk in today's era where we are generally talking about the high-rise buildings,
Sir, your screen is not
especially
visible.
when my
Screen is not visible.
Yes, sir.
Yes, sir. Share
Yeah,
entire
I'm
screen, sir.
trying. Just yeah, okay. Yeah, entire screen share. Right.
Yes, it is visible now.
Okay. I hope now
Yes.
it is visible.
Now it is.
Yeah,
Yes.
thank you so much. Okay. As I'm talking, when this particular topic is relevant, when we are in the era of now high-rise building, already in Gujarat, you might have seen
Tejas,
that
sir. Tejas, sir.
you can see the
Sorry to
high-rise committee has been
Hello.
established. Yeah, yeah,
Hello. Tejas, sir.
yeah. Please,
Sorry to
please, please.
interrupt, sir. There is one strip.
Hello.
Sir, there is one strip which is coming in between. There is one strip which is coming in between. Stop
Can you
sharing and
please?
hide.
Can you please hide? Yeah, yeah.
Is it okay?
Yes. Okay.
Okay.
Yes, sir. Now it is okay.
Yeah. Fine, fine. Okay. So when you can see in Gujarat, almost you can say so many high-rise buildings are coming up, and already the committee has been established by the government of Gujarat, and Professor Solanki is also one of the part of that particular committee. And lot many work is to be done in the case of Gujarat. Lot of you can see the site-specific studies to be carried out for such type of high-rise building. In this context, probably the seismic ground response analysis is very, very relevant. So today I'm going to talk about what are the different factors to be included while you can say one has to carry out, any site-specific study considering, you can say, the probable scenario of an earthquake in a particular region. So if you if you want to model any ground response analysis, or if you want to understand and effect of an earthquake, probably this three factors is very, very relevant. For example, if I talk about here, so then in this figure, you can see the first parameter that one has to consider, which is somewhere here, which is, you can say, where the earthquake happens. You can say it is a source parameter. Then after, the earthquake waves will be passing through the geological media, which we supposed to say as a path parameter. And finally, there is a small portion from which a local soil is actually going to affect this particular earthquake wave, which we are talking about the site parameters. So basically, if you can model this three parameter, 1, 2, and 3 together, then one can actually model the effect of an earthquake. If I talk about a contribution in this, then I would say literature says that the contribution in modifying the earthquake waves, almost if you take it is 100%, then this two factor, the first two factor, which is the source parameter and path parameter, which contributes around 40%, and remaining is the site parameter, which is in the context of engineers, which is very, very, you can say, local geotechnical parameters is influencing a lot to the earthquake characterizations. So in this context, you can say the ground response is very much relevant. Today, I'm going to talk about this third factor, which is the site parameter, how you can see the local site effect is influencing the seismic waves, and which is included in the ground response analysis. So if I talk about, very small, you can see the run the video, you can actually understand how this, you can say, how it is going. Can I put on this? It is not visible. Yeah, you can see this. Now, this is, you can see the some of the engineer buildings which has been founded on different types of soil profiles. You can see all the buildings are of similarly designed. All, you can see the story is also high. Only the difference is it is founded on different categories of soil. If you you can see the take little sections, I will actually move little quickly. You can see here, if you take a section here, then you can realize this particular first building is on solid bedrock where the hard rock is there. Second building is founded on poorly consolidated sediments. And third building, which is nearly the boundary between, you can see the poorly consolidated sediment and the water saturated sand, which is generally a coastal soils are there. And the fourth building, which is founded on very, very soft soil. Here, you can also visualize how the seismograph is actually going to record if you put the seismograph in those particular building in the case of earthquake. So if I run this through, if you can monitor along with the seismic waves, you can say how the seismograph is recording and what will be the effect that is being actually penetrating into those particular buildings, then one can understand the effect of soil onto this. So if you see the earthquake happens, the first wave which actually comes to the seismograph, which is the P wave, which is shown in the red, and it is passing through various buildings. The response has been recorded on the seismograph, you can see on the red line. Similarly, S wave has been reaching, which is considered to be a most damaging. And you can see how the building has been actually shaken horizontally. Then after, the surface wave will start coming and it will approach to each of the building. And one can also see its response on the seismograph, and at the damages which happens in a different categories of, you can see almost, you can see the some of the buildings is already failed. You can see here. So one can understand from this particular animation that if the earthquake comes and if the building is founded on solid rock, then generally it is going to have a high frequency type of motion in the earthquake, which has a low amplitude. And probably in this case, the building damages which generally low. But if you go towards, you can say the lesser material, less stiffness of material, as it has been actually becoming saturated, then in this case, there is a possibility that the earth will raise, you can say, the low frequency, and at the same way high amplitude. In such cases, the buildings is going to damage with higher damages. This also depends upon the typology of the building. Here I'm not considering the typology of the building. I will actually second animation I will try to show how with the different typology of the building will simulate this kind of effect. So if you understand the basics of this, for example, if you have, you can say, a natural frequency, you can see this particular bridge which is vibrating. Now generally what will happen is this particular bridge is having one natural frequency at which is always vibrating, and when the wind comes, and if suppose the wind velocity will actually have matches with the same resonance, same, you can say, the natural frequency, then there is a case that is the maximum amplitude will occur. And under this, it might happen that this particular bridge may vibrate with a maximum amplitude and may liable to fail. So this is a very basic concept of frequency. Suppose you can see here in a first, you can say, way, where the frequency means if you want to complete one cycle in 1 second or 1 unit, you can say how much time is been taken to complete one cycle. So if I take 1 hertz frequency, then generally one can say that the to complete one cycle you will take 1 second. Similarly, if I take higher frequency ranges, like if I go from 1 second to, let's say, 2 hertz, what is the just a small change? Like if you go to the 2 hertz, then this period will become lower, right? So it will come to 0.5 hertz. So that is only the changes that going to happen, and same has been actually applied in the case of musical instrument. To affect with high frequency motions, while you can see here, if you see the high frequency motions is there, it is vibrating in a very high, you can see, the amplitudes, but this boat is remain stationary, right? But in the same case, if you see, here is the amplitude is here is the frequency is very high. In this case, this boat is remain very stable while this is vibrating. So this entire behavior is also, you can simulate to the building. Like for an example, if you take 3 buildings, you a one small, you can say, building. This is a 10-story building, and this building is equivalent to the frequency, natural frequency of 1 second. And similarly, the high-rise building is having the frequency more than 2 seconds. Now, this is, as I said, this is also depends upon what type of the ground it is. So the seismic response is also dependent on ground. So for example, if I talk about a hard rock, which is also generate an earthquake of frequency which is less than 1 second, as you are going towards a softer sediments, generally it may happen so your earthquake frequency may rises. So under this particular thing, if you see the effect of those earthquakes, like for example, in a case of rock, in the case of, you can see, the soft soil, how this 3 typology of the building is going to behave. So the thing is very, very simpler. Like in an event of an earthquake, you can see here, this particular building is going to damage with the frequency which is less than 1 second, because when the less than 1 second of, you can see, the earthquake comes, it will matches with the frequency of building, and there is a chances that building will collapse. Similarly, if you see about these structures which will actually fail or collapse, 1 second will be generated. And similarly, this is also going to vibrate when the frequency, which is around 2 seconds. Now the question comes, when this kind of a frequency will be generated, what will be the formation underneath those buildings which will actually generate such type of earthquake motions, right? So as I said, as you have a stiffer material below the ground, then in this case, there is a chances that the higher frequency motion means the lower period motions which will be generated. So as in the case of rock, you can say in this case, if you see the rock type of stratum, possibly you can say the higher frequency of motion will be generated. It means it is the lower time period, and probably it will lead to the low-rise building is going to be damaged much. If you have a soft sediments, right, in this case, the higher time period of motion will be generated, means it is having a low frequency. In such case, the high-rise building is going to affect much. This may happen due to two things. If the earthquake is far-field and your stratum is soft soil. In this case, mostly your high-rise buildings is having highest vulnerability. And in just reverse of this, if you have hard stratum and if the earthquake is happened somewhere nearer, right? In this case, you will have a short period motion, and probably in this case, the low-rise buildings is going to affect much. So this is a very, very simple concept of ground response analysis that is to be considered. And in the event of an earthquake, if you just see here in a seismograph, this is the animation of 1985 Mexico City earthquake, which is probably a very, very famous for its local soil effect. And you can see here, the few of the building is going to damage. You can see how for a same earthquake, you can say for a different types of formation, you can say what type of motion is being generated. You can see the earthquake is same. This is having a two different type of formation. This is a rock type. This is a soft sediments. In the rock, you can see the amplitude which will be generated, which is quite low. While in this case, the amplitude is very, very high. And at the same time, it is the low frequency, means the higher time period. In such case, your high-rise buildings is going to affect much. And you can see this all red buildings is been actually collapsed. Other buildings is remain still during the same earthquake. And this is what exactly going to happen in many of the earthquake in the world. So this is what the basic concept all about. So if I talk, you can say I will show you one more small thing. Like for example, you can see here, this is a very simple figure. Like for example, you have one string or one, you can see the stick, you can say, which is a very, very flexible, over which you can put, you can see the mass. Now this particular, all the strings has been put in a such a way that the natural period of the building is remain same. Now, what we will going to do is, this professor is going to, you can shake this particular thing with a different frequency. And you can see how it is vibrate those buildings. So you can understand the same behavior is penetrating into our buildings as well. Like you can simulate this building is a high-rise building, this is medium-rise building, and this is a low-rise building. And you can see how this buildings is going to affect in an event of an earthquake. So you can see first one, like for example, now a low frequency motion has been given to this, and you can see this first one is vibrating very, very high in comparison to this two. Now, as you are increasing the frequency, you can see, then only this is moving very high, while this two remains stationary. So means now the frequency is been actually increased. Then you can say a low-rise building slightly is going to affect. If you increase very high, if you increase the frequency at very high period, then you can see this low-rise building is going to affect very high, while other remain stationary. And this is what the basic concept of ground response analysis, basically how the ground, different types of soil is generating which type of frequency and what is the typology of a different building. So, yeah. So with this concept, let me explain what are the different parameters that is to be considered while you are doing a ground response analysis. So the ground response analysis has many parts, so in which you need to use so many data. Like for example, if you have earthquake data, past earthquake data, then you also need to use the tectonic details. These two details which will actually help you to prepare the earthquake catalog for the region. Like for example, suppose you want to take the effect of an earthquake for past, you can say the 300 years, 400 years, whatever the data is available, you can generate the earthquake catalog for that particular region. And at the same time, you can also incorporate the tectonic detail into it, and you can prepare the seismotectonic map, which will actually help you to give an information about the what type of the earthquake, what magnitude of the earthquake, and in the vicinity of which tectonic features those particular earthquake happens, which will enable you to carry out the seismic hazard analysis, which can be performed with two ways. One is probabilistic seismic hazard analysis, and the technique which is called to estimate the peak ground acceleration model at rock level. So basically, you can generate the rock level value of PGA. Then this is the one aspect of this. Then secondly, in a second order, we are going to use the geotechnical data of the region, geophysical data of the region, as well as the certain geological information together, which will enable the entire region for the which will actually help you to carry out seismic site characterization process. Once you do site-specific characterization of the region, then the next step is coming that this particular geological information, which also useful to generate certain simulated ground motions. The simulated ground motions is only been generated when the recorded ground motions are not available. For example, if we talk about the Gujarat region, before 2001 event, you can say we don't have many earthquake stations available in the Gujarat. And so that if you want to analyze those particular, you can say the buildings or even the structural, seismic structural design also we used to do. That is also we are doing with help of, you can say, either earthquake recording from the other foreign countries. Generally, if you see the past literature, many of the seismic analysis has been done with Loma Prieta earthquake of California, which probably may not be true or may not serve the purpose or may not be similar in geology for the Gujarat region. And still we used to do because we don't have, you can say, the data. In such cases, you can generate the simulated ground motion histories. If you have a recorded histories available, then I think you can work, you can say you can do the ground response analysis with help of, you can say this recorded ground motion histories. So basically you have a recorded histories, you have all the geotechnical, geophysical, geological information, and at the same time you have the PGA model at the rock level. This will serve the input parameters for this particular ground response analysis. And from this ground response analysis, you can actually generate the design parameters for any type of, you can say the buildings, especially for high-rise buildings where the site-specific ground response studies is very, very recommended. Even this time a seismic code of IS 1893-2016 is also been recommending, that is the site-specific, you can say the studies for, you can say such type of high-rise building. If you go, you can see the specialized structures. If I talk about some literature review, I will not discuss much. But if I talk about a few literature review, then I think in most of the part of the world, this particular practice is existing. You can see many of the countries is when actually use this ground response studies and effectively calculating the local site effect at micro level. If I talk about in Indian context, what is the different, you can see these activities has been generated. So initially, this particular zonation activities has been actually started at national level. So where the almost we are doing the zoning in, you can say for at the national level, you can see this particular first map, which has been actually published by Geological Survey of India in 1935, where the whole India has been divided into 3 zones. First is the Himalaya zone, then the Indo-Gangetic basin, and then this peninsular India, which is shown in the white portion, which is based on certain parameters like Roseforel scale has been used, earthquake intensity has been used, earthquake damages has been used. There are so many parameters has been considered at that time. And based on the severity of the damage during the earthquake, they have actually made the zoning. And you can see here, there is a severe zoning, moderate zone, moderate damage, slight damage, and slight to moderate damage. As per the, you can say the Roseforel intensity of 7, it has been actually divided. Further, in 1962, the body of ISO, like Indian standard, has been actually established, and they have published the first map of seismic, you can say the earthquake resistant structures. That is in 1962, where the entire India has been divided into 7 zones. The least zone is zone 0, and the highest zone is carrying zone 6. The zone 6 is having, you can say, the highest seismicity, and which is based on the number of epicenters of an earthquake in the isosysmal maps, which has been actually taken into the consideration. And they believe the zone 0 means there will be no damage in those regions. And you can see this large portion of this particular map, which has been given a zone 0, and they are expecting there won't be any earthquake in those particular region. Then after the next revision came, and in next revision, you can say they found in this zone 0, you can say so many earthquake happens, and they created, you can say, a lot of damages. So finally they have revised those things, but still, but you can see the small changes has been happened. This zones has been actually narrowed down, and the minor to 5, where the zone 0 has been removed. So earlier, that is a belief, there won't be any damage in zone 0, but now it has been upgraded to zone 1, considering that there will be a damage in those regions, and so many earthquakes in that particular era has reportedly, you can say, the cause lot of damages. And so that this particular zoning has been actually upgraded. Zone 7 is been transformed to only 5 zones, which is zone, you can say 1 to 5. And then comes, you can say, the 1984. Still, this zone is, they've continued with, you can say, the zone 5, because there is no big earthquakes is been coming between 1970 to 1984. Only the certain structural changes they have made during this particular era, and they believe this particular map is fine. And this is what the map, which is, you can say, the final. But suddenly, during 1984 to 2000, we also witnessed 2001 earthquake, then the Jabalpur earthquake, Lucknow earthquake. So many earthquakes in between has happened, which necessitate to change again this particular zoning. And further, we have actually reduced this particular zoning. Zone 1 is totally abolished, and the whole India has been divided into 4 zones. That is from zone 2 to zone 5. So basically, why I'm telling this, why I'm telling the story that how the zoning has been actually changes. Even if you see this particular table is saying how the different estimated value with help of certain procedure that we are using, so many procedures to estimate the PGA value. Like you can use deterministic procedure, you can use probabilistic one, you can use analytical procedure, whatever you use. I mean, any method you use, and this is what the estimated PGA value from the literature. And if I summarize, like for example, 1995 Kobe earthquake in Japan, the estimated value is around 0.40 to 0.48, while the recorded value of PGA is almost double. That is 0.70 to 0.80. While if you say the 2001 earthquake, even our code is saying you take you can say the zone 3, which is 0.16 to 0.24 value, while the recorded PGA comes, you can say, in the epicentral region, which is around 0.5 to 0.6Z, which is much higher than the estimated value of PGA. And that is the same thing has been happened to the other region of the world also. And you can see this particular figure, which probably necessitate the further level of, you can see the estimation of this particular zonation. So a lot of activities has been started in nation with the individual researchers. So if I summarize this, then I would say they have published a certain maps based on qualitative aspects and the severity of the damage they have considered. Second is subsequent maps they have considered with the quantitative aspect and based on modified Mercalli intensity scale. And third comes, which is the probabilistic seismic hazard analysis. If you see those maps, probably you can say these are the maps which has been published by the various people. Like Khatri has published in 1984 based on probabilistic approach. This is one more, that is the NEHRP, which is the National Earthquake Hazard Reduction Program, has been started globally. And under this, for the Indian map has been published by Bhatia in 1999. Similarly, the Parvez has worked on deterministic aspect and they have also published a map. But you can see again, the condition remained the same. Whatever the values that we are predicting, which is giving the same story. So finally, it has been observed through this particular national zonation maps that it serves the first-hand guideline for the seismic hazard of the country. But the observed PGA is varies significantly because of local geological conditions, and hence which necessitate the seismic ground response analysis or seismic site response analysis at specific to the site, and hence this particular activities is being started. So now I would like to say that how this ground response analysis is to be done. So I have divided this entire, you can see the chart into the different segments. Like if I say the first segment in the first phase, let's talk about the probabilistic seismic hazard analysis, where you can actually find out the peak ground acceleration model at the rock level. So that is what I'm going to talk about. So I'm going to take the case studies of Surat as well as some of the pictures of Vadodara, where my PhD student has recently submitted his doctoral work. So I will take that particular thing also into the consideration. Like if you talk about a deterministic analysis, for example, this is the site at which you would like to find out the acceleration level. So first of all, you need to find out what are the different types of, you can say, the tectonic features around the city or around the particular site. So you can estimate those. In the second step, that you need to find out that in this, what is the distribution of the epicenters, and from which you can find out what is the maximum amount of earthquake which will be generated around each feature. Then in the second step, you are going to calculate the shortest distance use for that particular region. You can estimate the various ground motion parameters. So this is what the deterministic approach. But while I'm coming to the probabilistic approach, the thing is slightly different, because always in the earthquake, there are a lot of uncertainty which exists. For example, in a region, which magnitude of the earthquake happens, that probably we don't know. That is a big uncertainty. Second is this particular earthquake which will be generated at which distance from the particular site at which you are interested in. That is also a, you can say, the uncertainty. And similarly, there are so many other uncertainties which is pertaining to the site and other. So that is also this, all the uncertainties you can actually deal with certain probabilistic approach. And second advantage that you will get, the whatever the value that you are going to give, that is based on certain design period and also with certain frequency, certain probabilistic, certain probability of accidents. And so that which enables the optimal that you are actually giving to the designer for designing this particular city, which enables the designer to design this particular, you can say, the structures with optimal design features. So in a first step, as we have done in this case, just only the difference is you need to model the uncertainty. So basically the probabilistic density function that you are going to calculate for either a distance, for the magnitude, whatsoever it is. Then whatever the, you can say, predictive relationship you are applicable for the region that you are estimating. So which is correlating with those those probabilistic values. Finally, you will get this particular type of, you can say, the probability distributions, which is a Poisson's distribution, one can say. And then finally, you can calculate the certain level of probability of accidents for that particular region. So if you talk about a seismicity of Gujarat here, then you can see there are various maps has been actually published by Institute of Seismological Research. They are our neighbors, in fact, and they've published so many maps. And you can see here, there is a large distribution, large difference in the distribution of epicenters that has been visible. If you see the figure number A, which is the epicenters of an earthquake in Gujarat from 2006 to 2008. B figure is pertaining to the 9 years data, that is 2001 to 2009. Just you can see, if you see this two, and if I talk about only 1 year data, that is during 2008 and during 2009, how many earthquakes it has been generated in Gujarat, you can imagine how the seismicity, the different types of earthquake. Nowadays, we are often seeing in the newspaper that many of the cities, many of the towns which have been affected with the moderate level of earthquakes, especially in the Saurashtra, and also that particular thing has been actually shaking even in the South Gujarat. This is, you can say, the Indian zonation. Of course, in 2016, the zonation is not been changed, so I'm keeping as it is. So you can see the entire Gujarat has been actually zoned in all 4 zones, like zone 2, zone 3, zone 4, and zone 5. All is been there in, you can say, in Gujarat. Almost Kutch region is having highest seismic zone, while you can say this yellow portion is a zone 3, and subsequently this, you can say this, this color is zone 2 is representing. So my first job is to prepare earthquake catalog for the region. So almost we have used almost all the literature, and everything has been mentioned here. Almost all the olden paper right from 1883, even 1594 to 1975. You can see all the earthquakes which has been actually mentioned in those papers, which has been actually considered for this particular study. Also, we have contacted various agencies like Geological Survey of India, Indian Meteorological Department, International Seismological Center's website where the earthquake recordings are available. Even National Geophysical Research Institute is also recording the earthquake. Certain old record is available in our Gary also. Of course, in a manual form, not in the recorded form. ISR is now recording in digital form, and also the digital record is available in USCS website. All this information from 1820 to 2008 has been actually considered, and for even new updated catalog also we have published recently that includes up to date, means as on date data is also been actually updated. Then the second step comes in this is the declustering of the earthquake catalog. This declustering is required that because you need to subtract aftershocks, because aftershocks is concerned with a main event of an earthquake. So in this case, you need to remove these aftershocks and foreshocks from the earthquake catalog. So here there is 2 methods has been used. One is based on the temporal variability, and other is the spatial distribution, how the earthquake has been actually distributed in a spatial locations. So based on this particular 2 concepts, you can see this particular line is showing, you can say, the temporal as well as the spatial variability, and based on that certain earthquake clusters has been actually identified, and that has been removed, considering this is as a aftershock and foreshock event. And you can see this particular entire catalog, which is for entire Gujarat region, which is 350 kilometers around the Surat region, is been actually calculated. You can see this pink dots, which represents the various clusters, which has been removed, considering as a whatever the earthquake data we gathered for almost 300 years, past 300 years, which has been incorporated into the map. You can see here is the Surat or any other city that you would like to take, 350 kilometer radius. All the tectonic features has been incorporated into the map. Around that, you can finalize all this. You can see the earthquakes, where it has happened, what magnitude of the earthquake happens. So you can find out here, this is the MW 3 to 3.9, 4 to 4.9. So all this particular earthquakes has been actually put into the consideration. And how this you can see the earthquake catalog look like. This is the sample of few earthquakes which has been recorded. Then we have used, a lot of studies we have made nowadays. And at the time when we have done this particular study in almost 2012, 2011, at that time only the one predictive relationship is available, which is based on the paper of Raghukant and Iyengar. And he has actually found out recently at the time this particular predictive relationship, especially for Western Gujarat. And that particular thing we have used in this. And in fact, deterministic seismic hazard analysis has been actually carried out. In this deterministic hazard analysis, there are few parameters has been taken, like each fault has been actually identified. It has been given in notation. Length of each fault has been noted. Distance from the epicenter to the site has been actually noted. Around each seismic feature, what is the maximum amount of earthquakes has been actually generated, which has also been noted. And this values is been incorporated into this equation. And finally, with the uncertainty, this PGA value is been actually estimated. Then finally, this is what the seismic hazard analysis for the one point at the site. This particular thing has been actually considered into the probabilistic seismic hazard analysis by after finding out the sources which generates the significant amount of earthquake, like we have taken the PGA seismic sources which generate the PGA which is more than 0.01. And finally, this particular deterministic map has been generated. You can see that rock level, the PGA value which has been generated in the Surat region even, which is around 0.09 to 0.24, almost it is varies from zone 2 to zone 3, zone 4 even, right? For a certain type of structures. But this is deterministic. Of course, then if you go further, then the next step is to come, there is a completeness. Now, what do you mean by completeness? The completeness means, as you know, the instrumented data is available after 1960s. Before that, whatever the earthquakes is there, which has not been instrumented properly. And at that time, whatever the earthquake data which was available, either it is in intensity form or sometime you need to find out the intensity description in some of the even religious book. We know that, sometimes we used to say that, there is the earth is on the Sheshnag, and if the Sheshnag will actually move his head, then probably the earthquake is shaken. Or the small earthquakes that cannot be recorded. Though it happens in the region, but since we don't have the capacity to record those particular earthquake because of the sensitiveness of that particular instrument, we could not record it, and which hampers your catalog, so that the completeness has to be checked. And for that, we have used the graphical methods, which actually, if you plot the cumulative earthquakes, then you can find out that the continuity of this, which will give you the completeness of those particular magnitudes. So each clusters of magnitude is being checked against the completeness, and the completeness of the earthquake is been actually found out. We have also used a certain statistical method. Those statistical method, I will not go into the detail of those. Then finally, that particular, you can see the completeness is been actually calculated, and each method is validating each other. And you can see here, for each of the magnitude, what is the completeness interval in the past, you can see the years has been actually estimated. From this, there is a recurrence relationship is been actually calculated. Recurrence relationship which represents the seismicity parameter of the region. So basically, what type of the seismicity is been exist in the region, what amount of earthquake happens
Nazim,
Yes, sir.
can you please contact sir?
Yes.
Sorry.
Tejas sir, we had some discontinuity.
Yeah. I'm just doing it.
Yeah.
I think screen is not visible.
Yeah, sure, sir. I'll just do it.
Yeah, it is now appeared.
Yeah, okay. I think it just happened now. I mean, okay, fine. So as I'm talking, so first, if you find out seismicity for an entire region, for example, if I give an example, that if you find out the seismicity of a Gujarat which has certain seismicity, but in a Gujarat, if you see the different areas, like Kutch is having a highest seismicity, then the Saurashtra will come, then the mainland will come. So this particular region is having a different seismicity. How will you predict those seismicity from the regional level seismicity? So that is the procedure that is called as deaggregation. That deaggregation will find out the each seismic source level seismicity, and finally we can calculate that each source is contributing to what level of seismicity for that particular region. So this particular deaggregation process has been used with two parameters has been considered. First is what is the source length, and around this particular source length, what is the number of earthquake has been happened, or what is the number of earthquake has been associated to each source. This will give the you can say the weighting factor, and while you are multiplying this particular weighting factors, then the each seismic level of seismicity is been actually got, which will be the part of probabilistic analysis. This is the simple procedure has been actually used to generate the probability density function. You can see this, the first one is sorry, I need to come from here. So first one is calculating, you can say, the probability density function for the magnitude. You can see here the current magnitude and the you can say the lowest magnitude which has been generated in the region. Similarly, for you can calculate the probability density function for the distances or the epicenters. Then you can combine it up to calculate the value of you can see the PGA, and then after one can generate this kind of a hazard map for this particular region. So this is for the one single point or one single site. If you want to estimate this entire thing for the entire city, for example, at city level, then I think you can divide the city into number of grid points. So we have estimated for Surat, Vadodara, and even in Ahmedabad also we are working right now. So in this, we have divided the entire region into almost 10,000 grid points. And from this grid points, we have generated those maps. And from this map, PGA level for different value of seismicity. For example, you can see this particular map where this PGA at rock level is significantly reduced if you compare with a deterministic approach. And here, if you can see, this is having a probability of 10% in 50 years of accidents, which means, for example, if I talk about, let's say, any area, let's say this airport area, okay, and this airport area is coming around, you can say somewhere between 0.100 to 0, let's assume higher side, that is 0.105. So I would say at rock level, if it is rock is exist in this particular region, which is not the case, but still exist in this particular region. In this case, the generation of 0.105 of PGA that is having only 10% probability in next 50 years means 90% of the time in the event of an earthquake at rock level, the PGA which will be less than the 0.105. If I say penetrating into this, then I would say the 98% of the time my PGA value at this airport, probably this is something 0.160. So 98% of the time, my value of PGA, which will be in next 50 years, which will be less than the 0.165. It means my structure is safe. If you take this particular value, my structure is safe with 98% of time. So which will enables the designer to take an appropriate value of probability for the importance of the structures, right? Of course, this is at the rock level. So this is still is not usable for the city like Surat, because it is consisting of highly with the soft sediments, right? So further, you need to do the ground response analysis for this. So right now, I am just putting up this with the different value of probability. This is the map which will be generated for you can see the Vadodara region also. You can see here. So all the maps, similar procedure has been actually used. Of course, we have done certain modifications in concern with the limitations of past studies, and which we have incorporated. However, the output is look like a similar. So this is what the output with the different value of probability level for the Vadodara region, entire Vadodara city. Similarly, for different probability of incidence. One can use even this soil parameter into the probability, and based on this, you can say there is a coefficient has been given. If you use this, then you can actually calculate the response spectra for different site variations, and that is also you can study. But the major limitation of those graph is it is dependent upon the predictive relationship, and I found that this particular graph you cannot take into consideration, considering as you are moving from class C and class D. You can see this map and this map. This is class C and this is class D. Means this is stiffer, this is softer. Still, your peak is not been shifting. It is having a similar level of frequency. Means there is something wrong. Probably the predictive relationship is not be able to predict the you can say this particular frequency level for different category of soil, and hence this data is still not being usable. But of course, whatever the PGA value at the rock level can be taken for the further study. So this part I've completed. Now I'm moving to the second part, which is the seismic site characterization, where we have used the geotechnical data, geophysical data, and the geological information to carry out the seismic site characterization. So you can see this geological map of you can see the Gujarat. This is earlier map has been actually published by Mir, and then we have actually incorporated certain geological features, and this particular map again we have published. Where if you talk about a Surat even, where the Tapi is there, also this Gulf of Cambay is there, and you can say so many rivers is actually carrying the sediments. Here in this portion there is a Aravali is there. Here in this portion you can see the almost river is passing through the Satpura ranges, which is generally a basaltic rock. This basaltic rock carries the sediment of black cotton soil, which will be deposited in entire city. Similarly, the rivers which has been passing through this Aravali regions, which is also depositing certain silty sandy sediments, and which is also depositing in the Gulf of Cambay. While in the case of tides, which has been often coming in the Surat region, this sediments is also been actually depositing at various levels, and which is clearly seen while we are doing geotechnical investigation at that particular city. You can see here how the topography of the city has been existing. We have taken with the DGPS Artica, we have used in the entire city. We have moved around and we have finalized, you can see this is late long, and the elevation model has been actually created. And you can see this, the river has been actually passing like this. So this is little higher at altitude zone. And slowly as the river is merging with the sea, you can say this is a found it out, and nearer to the Dumas, the river has been actually merging, where you will find a lot of soft sediments. Of course, we have used a lot of geotechnical data we have collected from various agencies. Also, we have done certain confirmatory boreholes at the various sites. Almost we have generated 60 boreholes at different places. And also we have taken, as I mentioned, Hitesh Bhai has also actually helped me a lot to give a lot of data from his laboratory, so that all we have actually incorporated. And as I'm mentioning, you can see here at various places you will find this alternate layer of silty sandy layer as well as the black cotton soil, which is clearly seen this particular deposition is happening in all the regions. This particular model is being generated in the GIS, and how this you can see the fence diagram has been actually created, which is generated for entire you can say the location. Of course, this can be actually further revised with you can say the literal variation with the again finer grid, and one can actually see. Also, you can see the GST curves has been actually developed, which will be helpful for estimating liquefaction potentials. Certain region is actually coming, which gives potential of liquefaction mostly in the Hajira, and you can see the outer periphery of Surat, nearer to the sea. And you can see the SPT distribution. The SPT is very, very low in this entire region. You can see right from this left to this entire region, the SPT is very, very low. This region almost having, you can say, the high SPT, while other is the moderate zone. So 3 different zones has been actually one can divide based on SPT value at various depths. You can see here clearly at all the depths, this is actually values has been coming. If you talk about a water level, at that time the water level was somewhere you can say in the range of 0 to 4 meter in this entire region, and then you can say all the groundwater map is also been generated. We have also done, you can say, the seismic site characterization using geophysical studies, where we have used these particular instruments. So we have the seismograph, we have, you can say, we have performed MSAW test. So basically this kind of a geophones we have used. And we have used, 2 types of tests. One is the seismic refraction test, other is the MSAW test. And in fact, to generate energy, we have used this kind of a hammer, which is of 11 kg wooden hammer. And also there is a PG, that is a propelled energy generated machine is there, which can actually use for generating higher amount of energy. Whenever we are encountering very, very soft layer, it will happen that the energy is not been actually reaching to the last geophone. At that time, such type of the PG hammer we have actually used. These are the test locations. You can see in all the you can see the Surat as well as you can see the various places we have used this kind of a study where and this is how we have done the test. Like this is the short locations. For example, if I put the 24 geophones, then in between this, geophones, we are taking the shots for the MSAW thing. We are following the fixed configuration. One can use even the variable configurations also. One can move certain geophones and do the test. Then the seismic refraction test is also been used. Only the changes is the frequency of the geophone has been changed. In first MSAW, we have used 4.5 hertz geophone, while in the case of seismic refraction, we have used a 28 hertz of geophone. That is the main. Changes. It has been processed like the first arrival. You can see this lines, which has been manually picked up, which is actually showing when the wave has been reaching to the particular geophone. So this has been picked up, and from this, the travel time curve has been actually got. So observed travel time curve and time curve has been compared, and generally we have found out that with this we have ensured at all locations the gap is less than 5%, which will give the very nice readings. Even get, this will give operational wave velocity, seismic refraction test, wave motion, 1D model. Similarly, this has also been processed in in different software for techniques. Finally, for this, such type of shear velocity profiles, two-dimensional as well as you can say one-dimensional modeling is been actually generated, and you can see this has been plotted in the map for the various depth. Like for example, this 5 meter, and this is representing the same thing. This region is having a low velocity region that is along the river as well as in the western part of this particular city, and it has been demarcated by the different zones. So which will give an indication that under this particular soft soil is here, here is the medium soil, (20 meter, 25 on, of course 30 meter, and that way the entire, you can see the city has been characterized. Also the average shear velocity has been actually calculated, which will demarcate the entire region into different classes of soil based on the shear wave velocity profile. So this is nothing but it is called as the seismic site characterization. So from this you will actually able to know that which type of profiles has been exist in a city or at a particular location. You can do even location site specific study also. Then the steps comes is the synthetic ground motion here. So synthetic or the recorded ground motion. So that is the third step which has been used in the ground response analysis. We have a very is available. Strong motion accelerogram record, which is very essential for any type of seismic response study or ground response study. We have only this data is available for Bhuj earthquake, let's say. There is a strong motion accelerogram record at the basement of the Passport Office, Ahmedabad. And second is the spectral response recorder, which gives the acceleration or the spectral acceleration for the specific time interval. That is available for 13 locations, which is also been placed on a different types of geology. Only this 14 recording is available for entire Gujarat, which is considered to be in category of strong motion. And with this, which necessitate the generation of the synthetic ground motion using this particular detail for the validation of the parameters. So first what we did is we have tried to use the various models which has been existed in the which has been actually used by the different researchers. So we have started with FinSim is the model which has been generated by earlier researcher, which is Atkinson, and then finally there is one more addition to this with the FinSim has been modified by one more scientist who's called Basnev and Atkinson, and then after it has been further modified by Motazedian and Atkinson in 2005, and they have given the finite fault modeling code. So this particular code we have used, and finally we have used this entire strong motion recorded data for the validation of our things. So if I talk about, you can say this is how this particular code has been working, so which is based on so many parameters. I would say in summary, I will not go into the mathematical part of this, but just to understand, it will model 3 parameters. As I said in my first slide, it will model the source for the entire process. So if I talk about this here, you can see here the magnitude, latitude, longitude, hypocentral depths, deep and strike, fault length, fault width, rupture depth, subfault size, stress drop, all this in the category of source parameter. Then comes the 2 parameter, which is the quality factor and the geometrical spread, which is in the category of path parameter. What is the geology of path through which the seismic waves has been generated? And then finally, the site parameter, which has been represented with the kappa and duration, pulsating percentage, site amplification, and all this. For that, we have used a lot of literature, and specific to the site of interest, we have found out that particular parameters, and almost a lot of permutation combination has been actually used to finalize this particular parameter. I would not go into the detail of sensitivity analysis of this parameter class of studies which has been performed and find out the influence of each parameter into the final response of the earthquake. And based on this, finally, we have decided that which parameter influencing at what level. And then for each of the permutation combination is been used and it has been validated with the actual earthquake scenario. And then finally, that parameter has been actually fixed for the Gujarat region. So you can see this is the recorded data is available. As I said, this 13 locations where the wherever this particular SRR is been actually placed, which has been given an NEHRP class based on the geological condition. And as I said, it is recording the spectral acceleration at particular interval of time. Like this is 0.4 seconds, 0.75 seconds, and 1.25 seconds. This is also been used for the validation. Also, certain papers we have found out that they have made the attempt to find out the PGA with help of the seismological modeling or different approaches. So that is also been considered. So you can see here this dark dots, which is the values which is coming from our simulation. And when we are comparing with the studies of others, probably it will be coming in a way middle. So probably one can say it is almost an average value of all the other data. Then we have simulated, you can say, with our parameters, this is the simulated response spectra. And finally, these are the SRR recorded spectral data. When we put, it is coming in a very, very close agreement for various regions. This is pertaining to hard lock site. When we are taking a class C site, our simulation is being done for BC site, means the engineering bedrock level, while this is one level softer soil. So at higher frequency, it is getting amplified. So which is but natural. So qualitatively, this is also matching with our assumption. And third level, so that is for BC site and the class D, so which is further at a higher level of, you can say the time period. This is having much amplification in comparison to this. The PGA for the Bhuj region for entire Gujarat. You can see here how the PGA has been actually generated for entire region. Also, one more validation has been done that we have the isoseismal maps which is available for the Bhuj earthquake, and whatever the data of PGA we have generated, which is empirically converted into the intensity, and it is also been compared, and which is also matching very well with the past isoseismal maps. Also, you can say the PGA has been actually estimated with the different values, different analytical procedure is also been compared with the literature. Then finally, we have used the ground response. I'm not coming into the intricacy of, because I'm going to discuss in detail. So here, what will happen is the surface level ground motion. This is a recorded Bhuj earthquake data, which is available, which is available here at the base level. Then this is the strata of, you can say the soil at the passport office, which has been actually modeled. And when this particular earthquake is passed through this, the surface level motion has been coming. So which we are taking as a simulated history, which will be actually mapped with, response spectra has been mapped with recorded level. And you can see the recorded level of ground motion and the simulated level of ground motion, which is coming in very, very close proximity, which will say that whatever the parameter we have found out, which is correct, and one can generate the PGA as well as generate the history for entire Gujarat at different level of this. So if you put the seismograph at different places, probably you can generate this earthquake for region. So this is earthquake histories that has been actually found out. Similarly, we have generated various scenario, like for example, Surat city, what type of the earthquake can be generated. So if we analyze critically the earthquake distribution, we have found out that there is the earthquake of possible 5.5 to 6.3 can be generated. And then based on other parameters like source, site, and path, we have considered. And finally, the various near field earthquakes scenario has been actually generated, and numerous earthquakes has been generated and which has been taken into the consideration while we are doing the ground response studies. This is for Vadodara region. Again, in a similar procedure, we have analyzed the faults, analyzed the distances, what type of the earthquakes can be capable enough. Even the far field earthquake generate, you can see the lot of damages. What is the magnitude? What is the distance from which it has been coming? So based on this consideration, this entire mechanism has been developed, and finally the synthetic ground motion has been actually generated. So you can see here, apart from this, we have also used, you can say, certain recorded ground motion histories by comparing the geology of the particular site, and this natural histories has been actually used. You can see here that this particular thing has been representing the recorded ground motion histories has been actually how many, you can say, the natural time histories has been taken, how it has been actually compared with, you can say, the rock site or the geological criteria, and finally this has also been considered. You can see certain natural time histories has also been taken into the analysis. So this how you can actually complete this synthetic ground motion. And then finally I'm coming to the how you use this all this input for the ground response analysis. So if I talk about a ground response one, then basically you will get the output of the ground response analysis in terms of site response spectra, PG at the surface, predominant frequency, spectral accelerations, average spectral acceleration, or the response spectra for the different types of zones. This is what the output that you will get. Yeah. Okay. Now I will talk about several literature that what is the problem which has been existing in the past study while we are doing the site response study. So numerous researchers have used a ground response study in various cities of India. For example, if I talk the earlier one, which is 2004, in the study, they have estimated the shear wave velocity based on n value based on empirical relation of Turnbull, which is derived from is the transient motion, which will give probably false results, or rather, I would not use the word false, but I would say a lot of improvement has been actually needed, because at that time the knowledge was limited. Similarly, Nilima in 2006 has been used again for Surat. She has used Dectra software, but she has used the, again, as I said, Loma Prieta earthquake in the study of Delhi, which is not be suitable. So if I summarize, see all this people have used for different types of this, then I would say the first thing is, even for Ahmedabad also a lot of studies has been actually done. So but first is they've not used, you can say, the actual characterization at the particular site. They've not done the enough testing. They've used the empirical study without validating that particular empirical equation for the particular targeted site. That is the first problem. Second is, either they have consideration almost even in some of my earlier studies we have reported, even in touch we have done a lot of work professionally, where we have used site specific studies at this place. Even in this also, with our limited knowledge at that time, we could not also use so many things, and finally we have tried to revise those particular things. So basically, one-dimensional ground response, if you talk about, then it is having the basic assumptions. The first is the soil and bedrock surface are assumed to be extended infinitely in the horizontal direction. Means you are not picking up the lateral variations. That is the first thing. That is the first limitation. Second is all the boundaries are horizontal, and that response of soil caused horizontally polarized shear wave velocity propagating vertically from the underlying layers, right? So we are assuming that the shear wave velocity vertically. This is the flow chart that how you do the ground response analysis. First, let's talk about the input parameter. So as I said, the ground motion, acceleration, time history at the base layer, soil profiles in which you will actually get to know what is the thickness of each layer, what is the density of layer, what is the initial damping ratio, what is the shear wave velocity, what is the modulus, what is damping ratio. This all the things which will be coming. Now this ground motion, you can actually convert to the Fourier transform with help of FFT, which is known as fast Fourier transform method. And this soil profile with the damping ratio, which will give you the soil transfer function. If you multiply this soil transfer function with the Fourier transform, it is just a modification from time domain to the frequency domain, which will give you the frequency domain, as this is a multiplication. So this will give you the Fourier transform at the surface level. Then you can say the damping ratio and shear modulus value with the iterative procedure, and it in literature, shear modulus and damping curves is available. Even you can generate with help of, you can say, doing cyclic traction test at this particular location, and you can generate that particular curve for your type of input soil. So as I said, the first, if you model it well, so ground response is nothing but it is very, very simple. As I mentioned in this slide, I just go to that slide, so you will get to know exactly what is to be done. Yeah. So basically, it is the earthquake, which is being plotted with the rock motion. Once this earthquake is being actually plotted with this particular, see all these parameters, which is I mentioned, this all has been mentioned. You can take it as an input. So finally, if you put it this particular data into the software, as whatever the flow chart I have explained, that particular procedure they will do, and finally, you can actually get. This is the procedure of one-dimensional ground response analysis. And the same analysis which we have performed for this, and finally, these are the outputs that we got, this which I'm going to discuss this. Like for example here, you can see the first is the predominant or the fundamental frequency. You can calculate this fundamental frequency with help of this empirical formula, that is nothing but it is depend upon two parameters, that is the average shear wave velocity and the depth. Similarly, this fundamental frequency you can even calculate with help of actual ground response. Like for example, here for different locations, which is the average shear wave velocity has been mentioned through this amplitude versus frequency curve. So this is nothing but it is basically a transfer function that you are actually finding out. From this first nodal, the amplification, you can calculate this particular value, which is nothing but it is the predominant frequency of that site. Once this predominant frequency matches with your structural frequency, there is a condition of resonance you can expect, and you can actually talk about in particular region which type of the building will actually suffer most based on this particular frequency level that you can estimate. So this level is been estimated with help of, you can say, the actual ground response analysis as well as from the formula said, and it has been plotted together. You can see for most of the part, it is coming in very, very close agreement. Certain thing has been actually changes. This is just because the some anomaly in the data, which actually do certain, you can say, which is outside this particular limit. However, you can see most of the things which is matching. Similarly, if you find out fast Fourier transform, this is a Fourier transform spectra, which is at the surface. You can see there is a large histories has been used in the back. You can see in the magenta or slightly violet color, where, and this is the average one, and from this you can actually calculate the value of predominant frequency for the various regions, and this is also been actually plotted with help of predominant and fundamental frequency. You can see it is quite coming in a close relation. So this particular thing indicate that how the predominant or the fundamental frequency is to be estimated for one earthquake data or the earthquake data which has been used for the particular site, which will not be enough to estimate those value, which probably give you the misleading answers. So what we have done is this particular analysis has been performed for almost all the sites, and basically based on the frequency ranges, we have divided this. So as you know, this is the soft soil sites, which will give you a lower frequencies, and as we are moving from steeper sites, which will give you the higher frequency in motion, which is exactly based on this. You can see the entire cities has been divided based on you can see these regions. Similarly, you can also see at 30-meter level, we have given the input rock level, which has been estimated with the probabilistic scenario, and with input of this soil, how this particular motion has been actually modified. This has been estimated. This is with near field earthquake data, and also this is the same thing has been estimated with the far field data. You can see how it has been changing. The amplification has been changes widely for the far field data. This has been moving almost from, you can see, the 0.04 to 0.10, almost 2.5, 2.6 times the variation has been coming, while this is almost 1.5 is the amplification level has been coming for near field level. And various levels of the same thing has been actually coming in the Vadodara region also. You can see a lot of histories has been used. Natural histories has also been used. And this level has been estimated for entire. You can see here, this is the far field motions and near field motion, PGA at the surface level. And you can see the estimated value of the PGA that is for this region is varies between 0.150 to 0.400, even which is more than our seismic zone regions. So this is very, very essential while you are building up a specialized structures in certain zones, and where I think this data is quite essential while you are planning for especially high-rise structures. So similarly, for different cities has been actually calculated. Not only this, we have actually compared our spectra with IS code, and you can see this 3 spectra. One is for steep soil site, one is for moderate site, and other is for, you can say, sorry, this is for steep soil, this is for moderate, and this is for soft soil. And you can see as we are moving from steeper to the softer soil, our spectra is moving towards higher time period. Same thing has been actually happened in the case of Vadodara region also. And also, it has also been clearly noted that whatever the spectra given in our IS 1893, which underestimates the value for several frequencies, especially for long period motions, as well as for even certain level short period motions also. So basically, for a particular type of structures, like for example, you are planning for low-rise building to the high-rise building, in which particular area, which type of the building damages has been done. If you want to see those particular aspect, in this case, you can actually develop this kind of a graph where the various level of spectral acceleration with respect to time is being plotted. For example, this particular map says the spectral acceleration with respect to 0.1. So this map, while you are you can say the designing the low-rise structures, and you can take this particular value into the considerations. Even the codal, this SA by G, Z by 2, IA by G. Values has been given by code. Even if you don't take it, you can say structural period depending upon the class of building has been actually developed, and one can put here 0.7, 7-story building. This is 10-story building, and further you can say if you go for high-rise buildings also, you can estimate this. So this is for near field, far field earthquakes. Similarly, amplitudes, as I mentioned here, spectral accelerations for far field and near field earthquakes, average amplification factors. So as I mentioned, if you find out the average amplification, so again, if you see here, the average amplification is around, you can see this level is 3.5 for the soft soil. This level is almost, you can say 2.5 something. And this level is almost, you can say the 2.5 something. So average amplification also you can actually develop for all this particular region, where you can get an empirical idea that if the earthquake comes, then empirically how the earthquake waves is amplified in which particular type of region. So you will get a basic estimate in the region. Finally, In comparison to IS code, we have given, you can say, our own curve depending upon the classes of various types of soil as well. And this particular curve has been recommended over and above to the IS code for the site specific, after conducting the site specific study in the region. Now, this things is coming, you can say, see, this all the data is to be validated. And for that, you need an earthquake to validate those particular data. If earthquake comes, then only you can actually able to estimate and validate those particular data. So that is not the case always. So in this case, what we have done is we have developed, the separate procedure using microtremor studies to validate the entire site response data. This is the kind of equipment which has been available. So this is nothing but it is the triaxial sensor which has been attached with a recorder. You can connect this with, you can say, laptop. You can put this particular thing at the side in this way for a few hours. Like say you can keep minimum 1 hour to almost 12-24 hours, depending upon the accuracy of data that you need. As you put for a more time, that you will get quite reliable data. So as you put this particular thing, so it will measure the ambient noise from the particular site, and this ambient noise will pass through the certain formation, and this formation which will give you the predominant frequency as well as the amplification that you can actually correlate with your site response data. So for example, we have kept this particular instrumentation for almost 1 hour to 2 hours at the different sites. This is the one minute recording of each site. You can see this X direction 2, and this is a vertical component of the data. Once this is, if you put it for 60 minutes, then such type of 60 files will be generated. If you process it through, this is a flow chart. Basically, you need to take all these files together, process for the amplitude spectra using Nakamura techniques. You will get this type of curves. I will say this 3 nature of the curve, just to concentrate on, this is the H by V amplitude and versus frequency. You just concentrate on first peak. This is coming around 1 Hertz. For all the graph, this is coming around 1 Hertz, means lower frequency. As you are going for stiffer site, you can see this peak has been moving. You can see from 1 to, this is coming around 2.5 Hertz. You can see this. So it has been moving. This is again, you can see the stiffer, more stiffer site, where my frequency is ranging from, you can say, 4.5 Hertz, and it has been changing, you can say, quite a bit on a right-hand side. So this way, you can actually find out the different frequencies of a particular site. And if you plot it, this entire region has been actually divided based on the frequency ranges. This frequency and also the, you can say, the your amplitude will give you the vulnerability index. So this is plotted, and based on that also you can do the seismic site characterization with help of predominant frequency, vulnerability index, and you can also divide based on shear wave velocity, SPTN values, and finally you can demarcate into the various zones. This predominant frequency calculated with help of site response analysis or ground response analysis has been modeled with a ground predominant frequency has been calculated with Nakamura techniques, and it has been plotted, you can see, which is coming also in close agreement. You can see exactly at 45 line, a lot of values has been coming, which says the whatever the predominant frequency we have estimated and modeled, which is in close agreement with those. Even this is empirical values has been actually mentioned, that this is a VS30, that is 30-meter average value versus predominant frequency. I just missed the titles of this particular graph. So this is frequency, this is shear wave velocity, here is the ground response value predominant frequency, and this is the Nakamura value frequency, and which has been calculated. So in a nutshell, what I mean to say is you can conduct this kind of a studies, and I think a lot of potential exists nowadays. A lot of, you can see, the cities has been actually coming up. We are talking about the smart cities, we are talking about high-rise structures, we are talking about a lot of development in India. So even I think a lot of potential is exist. With this quote, I will actually stop my presentation, that even you don't know what high you can fly until you open up your wings. My best wishes to you all. I'm very happy if you have any questions to put. I'll be very happy to answer.
Thank you very much, Tejas sir.
Thank you, sir.
You have not put the efforts, but you have put your heart. I must say, you have not put the efforts, but you have put your hearts to give everything to our students chapter, and we are highly obliged by your talk. And I hope that students and those who have attended must be benefited. And what one request I should make you, that whatever your findings, particularly for this region or for these things, you are requested to represent to the BIS so that we will get the update data. Because now this is where we are lagging, particularly that we are keeping it our knowledge or everything in a book, but it is not represented in the benefit of a nation. So you are requested to give your comments, particularly what we have discussed during this talk, so that the things can be improved, because it's a continuous evolution. So particularly all the nation will be benefited by your experience and judgment. Thank you very much, and I request Jitesh Rai, Dr. Chavda, to summarize the thing. Thank you very much.
Yeah. So, we had this question answer session also. So, if there are any questions, then we can share some couple of time for the audience. If they want to ask any questions, they are most welcome.
Sir, I have one question.
Yeah.
Sir,
Go ahead.
near field and far field, this time history. So, sir, as we are entering the time history data in our Dixol software, right? So, actually, I'm considering the Bhuj earthquake, and my location is situated in Ahmedabad only. So, will it, because the recording station was also at Ahmedabad. So, sir, will it be a near field or far field for Ahmedabad, Bhuj earthquake?
See, if you are doing a study in Ahmedabad, and if the earthquake happens in Bhuj, naturally the earthquake epicenter is in Bhuj, and you are recording at almost 230 to 50 kilometers away from that particular epicenter. So naturally, it is a far field data.
Okay.
Right. So there is no there is no definition of near field and far field into the literature. But generally, we say that if suppose earthquake happens around, you can say, less than 100 kilometers, then generally we say that it is the near field earthquake. But if earthquake happens, you can say more than that, then probably we may consider, you can say, around far field. Generally, we are taking 150 kilometers and more. We are generally considering far field.
But sir, actually the recording station was at Ahmedabad, so it will record the waves at Ahmedabad only at that time.
But the earthquake is originated from Bhuj, right?
Okay, yes. So can we
so
consider
whatever the earthquake passes through this, so it will be a long period motion will be generated.
Because we have to scale down that time history to reach to the Ahmedabad. If we are considering it as a far field.
No, you don't have to scale down.
Okay.
No, you don't have to scale down. You don't have to scale down. Whatever the effect that you want to monitor on the Ahmedabad building, the recordings that, because it is actual earthquake has been actually reaching to the Ahmedabad. Why you want to scale down?
But at the Bhuj, the
Hello?
earthquake zone is zone 5, and in the Ahmedabad, the earthquake zone is zone 3.
Attention relationship will take care of that.
Okay.
See, ultimately, what you are talking, the zone 5 and zone 3 or zone 2, whatever it is, that is made by whom? That is not made by the earthquake. That is the man-made things. We have seen the effect, how the earthquake happens in different regions. how the damaging effect is happened, and based upon that we have demarcated as a zone. So it is nothing to see as a zone. So wherever the earthquake happens, it passes through certain formation, and that formation is created what type of you can say the damages. That basically is our concern.
Okay.
Just
Sir, I have
Saurabh,
one question.
please.
I hope you
Thank
got
you.
the answer.
Saurabh, please.
Yes. Sir, good evening. But first of all, thank you so much for a very interesting presentation. I have questions. I didn't understand much of your presentation. This is not my field, I'll be honest. But as a practicing
Okay.
engineer, I have two questions. Uh, First is
Ji, sir.
point of concern, sir. In practice, we are simply following the Z factor as given in the IS code. Now, one interesting thing which you pointed out in your presentation is that the actual PGA values which are being recorded in the earthquakes, you took the example of Bhuj, are much higher than what is given in the BIS code. So this is a huge concern, sir, because does that mean we are designing so many structures? In fact, even when we use for zone 4 0.24 PGA, customers
Hello.
will normally
Hello.
fight
So,
it's too high.
hello, Saurabh bhai. Actually, I just
Yes.
lost the connection in between. I could not
Oh,
hear
no
you.
problem.
If you can
I will
repeat,
repeat.
I can.
I think the one very significant point which you made, sir, in your presentation is that the actual PGA
Ji.
values as being recorded in the earthquakes, you took Bhuj example, are
Hmm.
much higher as compared to
Hmm.
even what the BIS is recommending.
Yes.
So this is a huge concern because in practice we are working on critical structures where even if I take like a 0.24 G as per IS, customers normally will fight कि ये बहुत ज़्यादा है इसको कम करो करके. So, but from your findings, it sounds like, does that mean that we are our design today is unconservative or risky even?
That is what I have requested to represent at the national level, so that and to finalize the thing so that people will be benefited.
Hello. Yeah. So actually, what you are saying is correct. See, so generally, whatever the IS code is giving the values, see, it is based on certain general assumptions. So for normal structures, it is advisable to take you can say the values which has been given by the IS code. But of course, when we are going for high-rise building or the specialized structures, probably in that case, if you see even in the code IS2, our recent code, there is a one line to go for the site-specific studies. And in fact, I would say, when we are working for the Statue of Unity also, with Institute of Seismological Research, and even one more structure has been coming in Ahmedabad. That is for Umya Mandir, Umya Dham. I mean, that is also a big structures which has been coming almost, you can say, the 150 story building. Where also we have done this particular site-specific studies, where we have found out this values has been actually coming quite higher than what has been actually estimated by the codes. And in fact, we have given that particular values, and we have designed, I mean, based on this.
I understand, sir, but in practice, the minute the contractors and owners, contractors figure out that site-specific से value ज़्यादा आता है, nobody will get it done. So this is a huge problem. It's a practical problem.
That is the human tendency, and particularly we Indians will not,
There is no choice, you
will
can
not
say.
come out of this. Yes, Jitesh,
Yeah, but I think
you were telling
as
something.
Hello.
Tejas sir, are you there?
Yeah, I'm here.
Yeah, I have one question.
Ji.
That is regarding the basin effect, like how a basin effect can be considered into our studies.
Basins means what you are talking about, sediments?
No. Basin effect, sites like for entire this Kutch region of Gujarat, they also have this basin effect. So whatever the analysis, if we do, even we do this ground response analysis with 1D response also. So whatever the effect will be there,
Right.
it may not be accurate. So because of the Bayesian effect, it may attenuate, it may detenuate also.
Yeah, I mean, see, there are various parameters. If you put it the parameters only, I mean, for example, you mean to say that we can say this basins has been actually how the topography of the basins has been moving. Am I correctly understanding?
No,
Please
the
correct me if
bedrock
I'm
level,
not.
yeah. If the bedrock level is, let's say the entire city is having somewhat bedrock level like this, and there is a full
Yes.
entire city is completely in a basin like Delhi basin. We have Kutch basin,
Yeah.
and so on.
So as you are saying, the variability of the bedrock you want to
Correct.
estimate, right? So yes, of course you can do that, but for that, you need to have, you can see the soil profiles for this. We have studied, you can say whatever we have studied and did the, you can say sensitivity analysis. In that, we have found out that the upper 30 to 40 meter strata, which gives basic amplifications, I mean, okay, and even it has been supported by a lot of literature. So basically, if you even take, the large bedrock, still ground response is not much changing. So even just, the upper few meters is very much important for this.
Okay. So that's what, again, like, as you have told that it has been studied based on the, like you told, like VS30 is more reliable. And why VS30 is not updated? Why we have not got
No,
to
we are,
VS 60 or something like that?
no, we are not saying VS30 is most reliable. See, nowadays, a lot of people are working to modify those particular aspects. Why we are taking first is whatever the initial course is there, which is based on VS30. That is number one. So if you want to compare your data with certain things, probably the VS30 measurements, which will be quite easy, and you can actually estimate whatever you've done the estimate, you can compare well with them. That is the number one aspect. Second is when we are doing, when we are changing, as you said about the basin depth and all this, when we are changing the depth scenario, after certain depth, the ground motion is not been significantly changed as far as the PGA or the high frequency motion is concerned. For the low frequency side, it gives certain, you can see the changes, which needs to be taken care in future. I don't know till now what level of studies has been actually carried out. But of course, it is having effect at the low frequency. But at high frequency,
Okay.
it doesn't carry. Means the PGA value will not changing much.
Okay, sir. And sir, again, the last question. Why still not the geological survey maps are not updated?
I think I'm not the right person to say. I mean,
Yeah. It is beyond his purview. Yeah.
Yeah. Okay, sir.
Okay.
So,
Sir, regarding the seismic characterization, I had a second
Ji, sir.
question. Why did you carry out seismic refraction tests, sir?
Sir,
What
we
was the purpose
did,
of that?
yeah, we did the seismic refraction test to validate our soils. See, number one is whatever the data we have, that is we have calculated, we have gathered from various agencies. Number one. Second, you can say we have MSAW data. So in fact, to reach to the certain reliable things, we need, as many as reference we will actually get. So we did, different types of tests on a particular site to validate each
Correct.
test with the others. That is what the purpose is.
But my experience of, I mean, I'm doing these tests in house. My experience has been that refraction testing is no good as far as determination of shear wave velocity is concerned. It only gives you compression wave velocities and depth of rock.
Correct, sir.
MASW, SSW, cross-hole, I can understand. Seismic refraction, I was very surprised to see because, you will not get any usable data, in my opinion, from it. And VP values, where in Surat, where you have shallow groundwater table, VP values also you will not get from any surface geophysics. You will only get shear wave velocity.
Yeah, absolutely. I'm saying the same. I mean, shear wave velocity that we have calculated from MSAW, just, that there is a qualitative assessment. Even the VP, even the refraction has many limitations. Like your profile should be, you can say, the stiffer and stiffer as you are going towards the depth. Your profile should become stiffer and stiffer. If you have, you can say, any low velocity layer, it will not actually pick up that. So that are all limitations. But if you want to grossly compare with certain things, I think it will be helpful. That is what the purpose is. However, we have not considered this particular thing into the analysis.
Jitesh bhai, you please now conclude.
Yeah. So it is my privilege to summarize today's presentation by Dr. Tejaskumar Thaker from PDPU. So he has talked about, I would not say seismic ground response analysis, but overall every components of hazard analysis. So as we know that, the major infrastructure projects in India, in our country, it is going on. So there is a need of site-specific, hazard analysis to be carried out, and accordingly the structures has to be designed. So that is what he has conveyed through his presentation. Then he has talked about the origin of the sources, then path parameters, site parameters, and then parameters to be considered for ground response analysis. He has made us understand that how the structures are going to respond to different frequencies. So, he had showed us a lot of animations also, that even it is not like that, if the structure is very near to the source, that means it is going to be affected maximum. No, it is nothing like that. It is totally based on how the frequencies at which the earthquake is going to come, at what magnitude, and what is the natural frequency of the structure. So he had made us understand every part very much in detail. Then he has talked about the seismicity of Gujarat city. Then he has discussed very much in detail about the seismic hazard analysis, in which he has talked about the earthquake catalog, declustering, completeness analysis using step method, CUVI method. Then he has talked about the degradation, aggregations. Then he has talked about the two case studies about Surat and Vadodara region, and he has specifically covered well in detail about Surat, where he has talked about the geological information of the Surat city, the SPT data, the elevations. He has talked about the elevation of Surat goes from 0 to 20 meter, then the soil grain distributions, then water level, then seismic site characterizations he has carried out using MSW refraction test. And yes, he has even discussed about the generation of earthquake motions for Gujarat state. And then he has discussed, then finally he entered into the ground response analysis, and he has discussed about 1D ground response analysis, which now gives us a way to think even about what are the 1D ground response and 2D ground response analysis, 3D ground response analysis, which can be taken up as a takeaway from here. Then he has discussed about the response spectra for different categories of soils in Surat region also. And finally, the very interesting part was that micro tremor studies, which has shown that we can actually determine the site's specific natural frequency of the the region. If you want to determine what is the natural frequency of that particular site, also that is also nowadays possible using Nakamura technique, that is micro tremor studies. So overall, it was a wonderful sessions, and overall seismic hazard package was delivered in this particular lecture. So on behalf of the organizing committee, I thank you for taking out time and delivering this lecture and covering every aspects of response hazard analysis.
Thank you so much. Thank you so much.
It would have been very interesting if this was happened offline.
We also wish the same, Alan.
Nazim. Nazim.
Yes, sir. Yes, sir. Hello.
No.
Yes.
Now,
Yes, sir. Yes, sir. We may end the session now.
Right. Thank you very much. Thank you everyone for being
Thank
with
you,
us.
sir.
And thank you Tejas bhai for an excellent presentation. Hope to see you and for guidance. Thank you very much.
Thank you so much.
Thank you, sir.
Thank you very much, sir. It was a really good session and informative session for us.
Thank you, Malik. Actually, my net is not working well. I don't know today.
Yeah.
It's always uncertainty is there with this network issue.
No, I'm in the office still. It is not working. It is I don't know. I mean,
Here also it is same
This
sometimes, sir. Like, when
this
we
is
deliver
this
the
is
lectures.
very rarely happens. I mean,
So sometimes we have to
okay.
even
Anyways,
take care with our mobile phones also. Like, sometimes we get a good network from mobile phones rather
true.
than taking it from offices.
Yeah, yeah, sure.
Sir, I have a question if you have a time. Hello.
I think Sir's network has gone.
Hello.
Sir, if you have a time, I have one question, sir.
Huh.
Sir, regarding the elevation of Surat, you have discussed about it goes from 0 to 20 meter. So the difference of elevation of 20 meter means that whether we should consider the typology effect into our analysis or not.
One has to, but this is a flat terrain actually, almost a
Yeah.
flat terrain. 20 meters you are showing, but actually I don't know. Uh, which is very very gradual. I mean, but
Mhm,
if you go towards this Ukai and all these places,
mhm,
then there is a huge topographical changes. Actually, in another studies, actually with the remote sensing, what we did in this actually there is a lot of variation has been coming where we are estimating even. Hello.
yeah.
We
You're
have
talking about
already
the variation.
estimated. I mean, yeah, sure. A lot of variation has been coming actually. Uh, Mostly from the eastern part to western part. If you go nearer to the Ukai, if you see, then a lot of variation is coming. Lots of variation. On east western, western side is almost you can see the deep. While if you go towards the eastern side, the altitude is raising like anything because you are going towards the Satpura side. So of
Sir,
course,
I
I
was.
mean,
How did you choose the study area as a Surat? Surat is seismically less, that much it is quite stable compared to Ahmedabad regions and all.
actually,
So,
I'm working mostly for low seismic regions.
okay.
My entire focus is on low seismic regions. Like whatever the studies we have done, if you see, then this entirely based on the low seismic regions, low to moderate seismic regions. Right from Ahmedabad, even Manali is also working. You can say in Dahej and Ankleshwar.
Ankleshwar side,
Similarly,
yes.
one more we have worked, which is Vadodara. Uh, and each time we are actually revising based on you can see the current knowledge. I mean, so see, low seismic region is most critical. See, for high seismic region, if you see like Delhi, you will have a clear demarcation. I mean, nothing to see. I mean, you can see the geology and you can demarcate the things. Like you have a rock,
Mhm.
you have a soil. So what is the microzonation? I mean, you can see the profiles and you can do so. While the challenges in the low profile, low seismic regions, one is the earthquake, which has been coming, which is low, though it is seismically very sensitive regions, right? If you see even 2001 earthquake, where the Surat is not been damaged, but I'm
Correct,
very
sir.
sure if suppose the this Hajira and all these areas has been developed at that time, probably the you will see you could have seen the damage there.
Mhm.
But it was at that time, fortunately, it was not so much developed at that time.
Correct.
So that is the thing.
Okay. Thank you, sir, for taking out time to deliver this wonderful lecture, and it was really interesting. And I have learned many things from your lecture today. So thank you.
Thank you so much. Thank you so
Okay,
much,
sir.
Jitesh bhai.
Okay. Okay,
Okay,
sir.
see you then. Yeah,
Okay, bye, sir.
sure. Visit us sometime.
Sure, sure. You too, please visit us, sir.
Yeah, yeah,
SVNIT.
sure, sure, sure. I think we'll meet. No problem.
Thank you, sir.
Yeah.
Okay.
Ankesh is
Thank you,
here
sir.
or
Bye,
no?
sir. Ankesh left, I guess.
I think.
Yeah, Ankesh is left.
Okay, okay, bye.
Okay, okay. Bye, bye,
See you
sir.
then. Yeah.